So I did a talk a small eternity ago about reverse engineering for beginners, which basically went over sort of your basic assembly, opcodes and instructions, and how to sort of identify certain code constructs, call types, and all sorts of things like that. So this is now the second part, where we're going to take what we have now forgotten and try and keygen a simple keygen file, which I got from crackmes.de, using Radar 2, which is a free reverse engineering framework, or open source, I should say. So to recap, so we talked about registers. Why is that white? Never mind. Keep going. We talked about the registers, we talked about general purpose registers, we talked about the other extended registers. So, you know, you have EAX, ECX and all that. You have the 64-bit registers as well. We talked about kind of what they're used for, to store data, to read data from, and also to sort of return values and pass values, and as well as the stack pointer as a register and the base pointer as a register. We talked about the move command, which basically allows you to copy data from one register to another register, from memory to a register, from register to memory, and from memory to memory. Conditional jumps, which allow you to jump to certain regions in the code based on the results of a previous operation. So you do a compare operation to see if this value is that value, and if then you have a jump if less than, jump if greater than. So it's like an if, you know, something else go to there. Basic math, stuff like add, subtract operations. And then I explained a bit about the stack, which is basically like a stack of plates where you push data on and then you pop data off the top. It's mostly used for local variables, stack allocated variables like arrays, but also for sort of unwinding the stack to go back to passing data to and from function calls. So today we're going to make use of that. We're going to use my tool of choice, Radar, because it's free and doesn't cost $1,000 or $5,000 like IDA does. And it does the job amazingly well. And we're just going to talk about a brief overview of that. Then we're going to take the binary, we're going to analyze it. Then we're going to reverse it so we're going to reverse the algorithm that generates the serial key from the name. I have actually got some notes. Hang on a sec. I'm going to just walk away. Just pass me my bag. I'm going to need that later. Right. That's it. And then we're going to write the keygen. All today. It's magic. So Radar 2, you can download it from radar.org. They have a very active development cycle, so always use it from Git. They have a point release every 6 weeks and a major release every year. We're currently on 1.70, something like that. But generally, if you use the version from Git or master branch, that'll be the first thing they'll tell you when you go to the channel and say, this doesn't work. They go, show me your version, update from Git. That's the rules. Yeah, so it actually stands for Raw Data Recovery. It was written about 11 years ago as a tool to retrieve data from a damaged hard drive. Then it developed into a hex editor, and then over the next decade it developed into the huge reverse engineering framework that it is. Inside you can debug with Radar. It's not the most powerful, it's not as good as GDB, but you can connect to GDB from R2 over remote machines or even local sessions. It's got an assembler and disassembler built in for a large set of architectures. Obviously the Intel, ARM, NES. There's developing for WebAssembly as well, an assembler and disassembler. Because it's command line driven, it's entirely scriptable in Python, and as well as I think they're adding Lua support now, and obviously R2 script. And there's like a lot more, but we're not going to get into that. I mean, it has a ROP gadget search features and all sorts of nice tools that we're not going to cover today. But you know, check it out if you're interested. So our binary is a very small binary. It's rated level 2, which takes a bit of brain power. I think that's the definition. It's actually much easier than that. It's fairly straightforward. Crackmes.de is down at the moment due to some EC regulations they have to change some of their website things. It's been down for months. So this is a link to a 500 meg zip file that contains all the Crackmes as of 2015. So if you want to download all of them and have a play, that's one place to go. It's a 32-bit Linux binary. It's compiled with NASM, so it's actually it's written in assembler, which you might go, well, that's going to be much harder, but it's actually a lot easier because there's no system libraries or anything like from C or API calls. It'll just be pure assembly. It'll be quite nice and straightforward. As I said, no external libraries. It doesn't call into any printing functions or any API calls, and it's very simple. And I'm going to have a demo. It's all going to go wrong. I want to sit on the head thing. So, right, let's close this. Find my mouse pointer. There it is. Right. Can everyone see that? Yeah, good. Right. Right. Okay. So in here is the keygen me. So we're going to try and crack that. So if we just quickly run it by having, this is sort of our initial analysis, if you will. That's when there. So it prompts us for a username. So if we enter a username like this, and then it asks for the password, and we say no, try again. So then we'll try a couple of, so like we see that are short characters, or at least numbers. Let's try D. Yeah, so there's obviously a check for, you've got to have a minimum length, and possibly, and also a maximum length. So we know that we can work out how long it should be, but we're going to be looking for somewhere where we're going to see, is the username a minimum or maximum length? There doesn't seem to be any checks for numbers. No, so yeah, there's only literally, that's a couple of things. We'll see some text. And that's basically all we can really look at this point in time. So let's launch it in R2, keygen me. Right. So what the first thing we can do is we'll get all the file information out of it. So we can see the architecture, its bits, its bin type, whether it's got the stack canary enabled, if it's a little or a big endian file, what language it is. I mean, the language is C, but it is assembler, what machine it was compiled on, and everything you kind of need to know, just to give you an idea of what you're going to be dealing with going forward. Another thing that's quite good to do is look at the strings. So these are the strings that, oh, no, please, no. Oh. Where is it? Why does it do this to me? Help. Ah, okay. So they're the strings. So this is like if you run the Linux command strings, it tells you what strings are in, but this has the added advantage. It gives you the actual address inside the binary where those strings are located. What you can do from there is you can actually then use this to find locations. So if you know your binary is running a certain piece of code with a certain string in, you can then look where that memory address is accessed, and it will show you all the locations in the code, which I will show you, well, I might as well show you now. And the way we do that, so we see, is it two? Yeah, so we see the top one here, the keygen NASM, that's the title. That's at the virtual address at the top. I'll point with the pointer, makes more sense. So what we can do, we do AXT. I think I might need to analyze the binary first, but let's have a look. Yes, so we do analysis, so that analyzes the flags, bytes, function calls, and constructs some function names for us, which is like just a shortcut. So here we see, this is the disassembly that accesses that string, which basically moves that string into ECX, and it's used at 804, 808A. Not much use with the assembly ones because, as you can see, the good luck string and the nope string try again and all that is one long string. So normally there'll be separate strings, but in this case what they do is they just print out a chunk of the string. We can then look at where the entry point of our binary is. And the good thing about R2, it drops us actually at the entry point. If you're running a C binary, you'll not be at the main function when you come in. You'll be at the actual entry point because there's a prelude to loading a C binary and a lot of things can happen in there. So for the sake of completeness, you actually get dropped into that starting point. And then, yeah, we do the analysis. So if we do AA, and the question mark will always show you the commands. So AAA will auto-name functions after AA, which is analyze all flags, which are basically like the functions, if you will, to some degree. So, and then, so if we look at the flags, so the flag spaces, we see there's the string, symbols, and sections. And if we do print the, is it symbols F? Yeah, so these are the symbols inside. So there's a few actions and there's the strings. And then for the actual strings, that's probably what I just typed though, isn't it? The symbols should be something different. Okay, there's probably something missing at the bottom, which I can't get at. But anyway, so yeah, so that's basically the sort of initial getting a feel for it. So if we now look at the disassembly, that's it. That's the binary. So at the top, you can see 4 move commands and then an interrupt call to AT. That is, if you're not familiar with assembly, that basically is an interrupt to perform a system call. And the system call is defined by what value is in EAX. And then the EBX is the output, ECX is the contents, EDX is how much you're printing. And how do I know this? Well, I'm going to move this window, and we're going to lose content again, I think. I just want to get the bottom of this window in. Mouse. No, not yet. Right. So if what we can do, oh Christ. Right, so we see that EAX4, that's our syscall type. So if you can see at the bottom, unfortunately it is at the bottom, we do AS, which basically does show current syscall and arguments. Well, we can actually just do AS, no, AS4. We see it's actually a write. So, but the better way to do it is to set asm.mu equal to true, which is a setting. And then it actually tells us exactly what it's doing here. So we have a write, and you still have to know what 1 is, but that is standard out. It tells you the string it's going to write out and the number of bytes. And then again, it does it here for the username. So this basically is the setup to print out the prompts that we saw at the beginning. And then down here, the EAX3 is a read. So now we know that once the prompt is happened, we're going to enter our username. It's going to be stored in lock.user. And it's a maximum, and it's only going to read OXF bytes, so 15 characters. And then the next thing was I'm just going to turn off the asm.mu equals false, because then we can do a nice thing. Cursor mode, and so here we can see that we compare. So after a system call, the amount of data written or read is returned in EAX. So what we're doing here is we're saying compare the value in EAX to 3, and then we've got the conditional jump of jump if less than or equal to nope, which I guarantee you is where we say, no, that's not right. So we now know it has to be more than 3. So we can leave a comment, username min length 4. So we can leave a little comment here for later use. So now we know that. So then we store the value in EAX, so the number of bytes or number of characters of the username on the stack. So we push that on. Then we compare it to OXE, which is 14, and then we say we've jump if greater than to nope, E to nope. So we know that the username max length is 13. So that's our next thing. And then if that all goes well, we carry on to here where we print out the password prompt, and then we have another read down here. Hang on, let me just scroll up here, where we read up to 15 characters from the password. And then so we only read 50. So if you have a longer password, it'll just discard what's at the end. Then there's a pop EBX. So what that will do, it will pop. So if we go back up to the push, so push username len onto stack. And then this will pop username length into EBX. So now we've got the username length in EBX. And now we compare EAX, which is the length of the password, to EBX, which is the length of the username. And then we do another test to see if they're not equal, then we go to fail. So the length of the username and the password has to be the same. So username len equals pass len. Let's do it like that. And then we push EAX. So we store the length of the password length is stored in EDI, and then we push that again onto the stack. The 4, let me scroll down, the 4 XORs up here basically just zero out those registers, so they're just going to contain 0. And then we pop the stack into EDX, and that is what we pushed up here, so that's the password length again. So EDX contains the password length. Now comes something that I covered in the last time, which is a for loop, which we can identify by these handy little arrows that will keep going round and round. So, and also this cipher tag is very helpful to let us know that this is where the business is. Okay, so the username is moved into ESI, and we also move 5 into the lower half of the EAX register, which is 8 bytes. Is it 8 bytes? The lower half, the better half. Okay, and then once that's all set up, we enter the cipher function, or loop. First thing it does, so we know ESI contains the username. ECX is 0 at this point because it was zeroed out up here. And this will give you the offset into that string. So it's basically an array index. And that gets moved into the lower half of EBX, which is then moved into the upper half of EBX. So the EBX 16-bit register, 32-bit register now contains the character at the bottom and the top half of its register. We then OR BL, the first character of our username, with AL, which is 5, because it was set up here. Then we move the high register, the high half or the top half of the EBX, which is the unchanged character of the username, into AL, into the lower half. And then we move that changed ORed value into the username string. So we're basically replacing the first character of the username with the same character XORed with 5, not XORed, ORed with 5, and then just replacing it. Then we increase ECX by 1, and then we compare ECX to EDX, which is our line length, our password length, and it's decremented here by 1 because obviously you don't want the terminating null. And then we see if jump if less, we carry on. So basically this is your while there's still characters, carry on looping and oring values. But what's important to notice is that AL is no longer 5 after the first iteration. It is now the original value of the first character. Right, so if you start with 5, you OR that character with 5, the next character gets ORed with the previous character, and so on. And then when we're done, we clear out EBX, we move the password into EBX, clear out EAX, and then here is another loop where we basically, to cut it short, is we iterate over the password we supplied and the ciphered password generated by the above loop, compare the 2 bytes, and if any of them are not equal, we jump to fail. We decrement the loop counter, we compare it to 0, so we're going from back to front. And if we're still okay, we loop again, so we go through here. And if everything's okay, we go to yep, and we get success. So if you want to look at that in, nope, not like that, like this. So this is a ASCII graph representation of the code. So you see the block up there with the prompts, and then the first test down here, comparing the username length, and there's a true and false path. So the true path will take us down to here, which is the nope, which, as you see, prints out, this doesn't seem like a username. And yeah, so we follow through, we check the maximum length, we check the password, and we clear out all the stuff, and then we enter our loop. And you can see by this nice little loop indicator that this is the loop that ciphers it. Then we go through, we have another loop iterator here, sort of, to some degree. It's not quite clear how it's drawn, but if it's false, it goes to then loops back round. So, and otherwise it goes to nope. Then if we finish here, we go to yep, which prints out, good work, I hope you keygened me, and we feel good about ourselves. So, everyone follow that?
Sven, just a question. Can you just think of a programming language different from some programming language that produces this code? Because just to shift through the registers, but basically, I don't think a compiler could use it, would it?
No,
even if you put half, if you put, I mean, maybe in 32 or something in C, that the shift would look different, not blockwise, but bitwise.
Well, I mean, it's taking the string and you're basically iterating over the characters. So you could write that in C and compile it down.
Could, but it wouldn't use. Would it use the a low and a high just as a? They shift through.
It might do.
It might.
It's hard to really see. It's hard to know what the compiler's going to do at the best of times.
Yeah.
So.
I'm just guessing because the switch from half.
It does happen. It does happen.
32 bits is just.
Yeah, I mean, it's just because it optimizes the usage of the registers. You're not wasting that space.
Looks tuned.
Yeah. Okay, so we can write the keygen, or so basically what we've done is we figured out roughly what we're dealing with. It's a very simple thing. I mean, I think so anyway. It's not. I've seen a lot worse. We've looked at the basic structure, we've figured out what it is, we've identified some of the strings and where they're used, areas of interest to us, and then we've stepped through, we've followed through where our data's going, what's happening to our data, how it's used, and then we identified the cipher function. We worked out step by step exactly what it's doing with our data, and then, to cut a long story short, we can generate a keygen, which basically looks like that. So we ask for username input, we set our value to 5, we have a result array, and then for every character in the username, we store the original, we OR it with the original value 5, we store the integer value of that original one in val, and we append the encrypted value onto our result, and then we just print out the result. So if we just never ever install 2 versions of Pythons on the same machine. See, it just doesn't work because it needs to be 3.5. No. Trust me, it works. It's straightforward, but then yeah, you can basically type in your username, it gives you the password, you enter it into the keygen, and you're away. Now, what you can do, have I still got a thingy open? I do. We did all that, and then we profit. So basically, the summary there is, this is just a very simplified view of what reverse engineering is like. So you'll be given a program, or you'll be given some sort of software, and you need to figure out, you want to do something, or you want to remove a nag screen, you want to create a keygen, you want to just change the fact that this pop-up comes up every 5 minutes, or you want to just change the text to something that really bugs you. You can do all that. Or maybe you want to just go in and find out how this thing works. It's a proprietary API. You don't have any documentation. So you can go in and you can reverse engineer. There's a great book, Practical Reverse Engineering, where it talks you through reverse engineering an undocumented Windows API and how to initialize certain things. In real life, you're never going to see anything like that. It's just, everything is going to be huge. There's going to be so many system calls, so many API calls that are just going to like obscure everything. But you know, it's just training yourself to find the right places and identify where you might want to be in the code, so that you know where you're going. You can also dynamically debug this. I mean, you can look at the code and go, okay, here is where my username gets used. You put a breakpoint on that. You watch the memory. You step through it, and then you can see how your result is changed, and then you can it helps work out what it is. But the advantage of doing it statically is that you can do this with Windows binaries on a Linux PC, or you can do ARM binaries on another platform, so you're not restricted to. So yeah, and similar stuff is used for malware analysis, defeating copy protections to analyze and find potential exploits, and capture the flags a lot of the time. So yeah, so basically all you really have is learn assembler, at least basically what the commands do, the instructions do. You don't have to be able to write it, because I can't. Learn some basic programming idioms like, you know, for loop, switch statements, that gives you a feel of how to identify them. What is good practice is writing small programs and then compiling them and then looking at the assembler in the debugger, or just compiling it to assembler through GCC. And yeah, just practice if this is something you want to have a look at and stuff. So, any questions?
Do you find the lack of a graphical interface can be a hindrance with larger binaries? I can imagine that if you're trying to do like a targeted thing, like bypass some kind of check, you can zone in and it's good. But if you've got like a bit of malware and you're going, I want to understand all of this, do you find that lack of graphical interface where you might be able to, you know, on some other commercial, you know, for example, products, be able to click on something and it will nicely take you to that bit? And do you actually find that a hindrance?
Well,
is it just, you know, getting used to it?
It's knowing, I think, how to work with it. I mean, if I just do this, and we look at so you can see down here, so there's JLE location note, right? And there's a little 1 there. If I press 1, it takes me back. And if I press U, it takes me back to where I was. So there's a lot of ways you can manage the workflow. The ASCII graph this always just shows you a block that you're in. It doesn't actually show you the whole code.
Right.
There's also an option to export it into dot format, so you can have a PNG for the entire call graph if you wanted to.
I've used IDA Pro a lot, and the thing is you get lost when you start clicking through because it doesn't really let you get back to where
Right.
you were, because it keeps bringing up different tabs.
Okay.
Like this as well. And so it's like, well, actually I started over here in this tab over here. And then
Yeah, this is like one place, and like I said, you press the numbers to follow the thing through. You can even press them here. Well, there isn't one. I know there's a couple of tags.
Yeah. Also, just as a note, there are quite a few GUIs for radar. And,
Too many.
Yeah, and just one came out recently, which is supposed to be really good.
Yeah, something named after a samurai sword.
Yeah, I can find anything else like that.
It's
But
not. Yeah, it's I don't know.
I don't know.
But yeah, it's actually it's one of the more promising ones.
It was like I saw 5 or 6 people like that are in reverse engineering stuff like that, like that are in the security space, that they were saying that it is like the most decent up till now.
Yeah.
Are GUI, but
Yeah.
I haven't seen it. So
Yeah, it's a cute C++ thing. I think it works on all platforms at the moment. So, but the problem with the GUIs is that you're always going to be some versions behind. So he's basically got R2 as a submodule locked at a specific point, whereas like main development just carries on. So you're always going to be a few weeks or at least behind the actual official release.
From my perspective, it's like the GUI, the only thing that adds is the fact that you don't have to remember all different shortcuts. Like that's the annoying thing.
Well,
like with GDB.
You don't. You've got help.
That's the thing. If you don't actually print it and have it right next to you and seeing it every single time.
Well, you need to go to Pen Test Monkey's cheat sheet for R2.
Yeah.
There's a lot of resource. I mean, yeah, it's a learning curve. It's like Vim. I mean, you don't sit down in Vim and go, I know how to quit this. You kind of open it up.
Like,
Yeah, exactly. It's exactly like Vim. But I mean, so here, what's nice? What's nice like Vim is that all these are. It's like a progression. So, like say analysis commands. Okay, so we get a question. A question mark. If I can actually type. And then we see, okay, so we can analyze bytes, and then we can analyze n basic blocks and analyze opcodes, and we can output graphics.
Fine if you know that what you want to do starts with A.
Well, yes, but that's the whole thing. You start there and not.
Now we do B. Now we do C.
So yeah, I mean, you go A, analysis command. So you want to do analysis. You go compare block with given.
one for every letter.
Yeah.
Oh yes, of course.
Imagine there's some crowbars going on there.
If you look carefully, it actually had to go to uppercase as well.
Yeah.
Oh yeah. There's, I mean,
you can always have a second window, a second, just a second tab on your terminal.
yeah, exactly.
One in
I mean, what's also nice, it has.
I mean, it's the same as if you have a GUI. Then it's only the black background. But
Yeah.
You have this one. You can change this one.
I mean, everyone, it's like they see this and they go, oh, in the channel, it's like, oh, there's just too many commands. I don't know what to do, and you're like, people just go, just press this, and you're like, oh.
How many of those do you actually use regularly? There must be like a subset of.
Sorry?
There must be like a subset of 5, 10 maybe. That you
Depends what you do. I mean, if you're like just reversing stuff for fun, probably only a little. What I used mostly. If you're looking at malware analysis, probably a bit more. Then if you're looking for exploit development, you'll use a whole different set. I mean, it depends. I mean, it's got a lot of value as well because it has like the built-in assemblers as well, so you can it assembles as you type, which is quite nice. Don't ask me to do that because I've forgotten how. But and it also comes.
So that would be good from a learning point
Sorry?
of view. Good from a learning point of view. It assembles what you type, and then you type in a high-level instruction, and it would just.
No, you type in either the opcode or and it will give you the assembly instruction below, or you type in the assembly and it gives you the opcode as you type. So, but there's also
Pretty much a NASM translator. all the flags.
Yeah, as you're filling in the opcodes, it can disassemble those in real time, kind of thing. So, like RASM is the assembler disassembler, and these are just some of the these are the architectures it can handle, including.
It had Mojang's.
It had what?
Mojang's, whatever it was. You know, the fake thing he built for that game he did at Brilliant.
Which one's that?
DCP-16. That he
Oh,
was
the.
going to make a computer game, wasn't he?
Yeah, they're pretty.
Computer.
They're pretty keen on being able to assemble and disassemble, or at least disassemble everything that's interesting to someone. And then there's also a plugin manager where you can install other assembler plugins and whatnot, like Unicorn and Keystone assembler or disassembler. And yeah, RASM 2 is basically just, you assemble x86. So we do MOV, EAX, ECX, and then you get the 89C8 opcode out, and then you can do the same with disassemble x86, and we just give it 89C8 without the quotes, without any symbols, and then you get the normal command back. So, I mean, most of the work I do is in the assembler disassemblers. So I did the full rewrite of the x86 one, and I've just reworking some of the ARM stuff, which is getting so fucking popular thanks to the Internet of Shit. It's like everyone's going, ARM this, ARM that. And I go, no, it's hideous. Too many arguments. But anyway, yeah. As I said, download it. It's as easy as so that's the Git thing, the Git repository, and there's a sys folder, and all you need to do is do sysinstall.sh, and that will update it from Git, build it for you, and install it system-wide, or you do sys, I think it's user, yeah, sys user, and that will give you a local copy. That's how easy it is. Yeah, and it will build on pretty much anything. They've got it running on a Pebble smartwatch. There's an Android tool as well. You can run R2 on your Android phone on a Tmux shell. Termux shell. Yeah, and contribute if you're in any way inclined. There's lots of work that needs to be done. Yep. Cool.
Yeah, thank you very much.